Welcome back. In this next video, we want to continue our progress into the process of exploratory data analysis and now talk about how we want to summarize a data set numerically. You'll want to pause the video at this point and download the following two data sets and import them into StatCrunch if you have not already. So we're going to talk about what are called summary statistics. These are numbers that summarize the data set, and statistics we know are things that we compute from a data set. So these are numbers that we compute from a data set that are going to summarize the variable in some sense. And a little more specifically, what they're going to do is they're going to capture the main features of the plot. And it turns out there are two numbers that we want to compute that are going to give us information about the plot. And those are the center of the data set and the spread of the data set. And we're going to look at those each now in detail. So first of all, there are three different measures of central tendency. And what that means is there are three different ways that we can specify the center of a data set. And those are the mean, the median, and the mode. And the 5 questions that we want to answer about them are, first of all, what are they? We're going to define each. How do we compute them in StatCrunch? How do we interpret these values? And this is the really important part. How do we know which one to use? We have 3 different measures. Can we use them all? And why is it important? Why do we even care about this? So first of all, the mean is just another word for average. It's the statistician's way of saying the word average. And of course, what we do is we take all the data values that are valid after we've cleaned the data, we add them all together and divide by the number of data values. And of course, we rarely do this on our own. We always use StatCrunch because this is a very laborious, although it's an easy calculation, it's very, very time consuming. We generally denote the mean with an X with a bar on top, and we pronounce that X bar. So this is the sample mean. The median is just Q2. It's the second quartile or the 50th percentile, and we talked in the last video how we can obtain that. The mode is the value that most commonly occurs, and we generally do not specify the mode. And the reason why is it depends a little bit on how the data is generally grouped in a histogram, and a single value occurring most often is really not very reliable. So we're not going to use the mode at all as far as the center of the data set. Now we are interested when we talk about categorical data, but for quantitative we're not going to use it. So how do we compute them? Well, we use StatCrunch. And we're going to go to stats, summary stats, and columns. So your view would look something like this. On the top menu, you'll click the Stat tab, and we're computing summary statistics. And we're computing them from columns of values. And once you click on that, you'll have a new menu that will open. You're going to go ahead and click whatever value you're looking at here, okay? Click on the statistics you're interested in and hit compute. And if you want to choose more than one, you hit Control-Shift to choose others. That's on a PC. On a Mac, it'll be a slightly different command. And then you'll get a window that looks like this. And I want to go ahead and do this for the home run data. So this data that we're looking at gives the number of home runs each baseball player hit back in 1920. And for right now, let's just look at our variable home runs, and we'll compute the mean and the median. So I'll go to Stats, Summary Stats column. I'm just going to look at home run, although I could choose more than one. If I hit Control-Shift, I could do RBI also, but I'm not going to do that. And I'm going to click the mean. And then I'm going to use this little bar and scroll down. And I'm going to hold the control button and then click median. And that's really all we need to do. We don't have to worry about the rest of these. And we get this nice little summary. And so this tells us that the 50th percentile is 0. That's fascinating. Now, of course, we would have, before we did any of this, we would have sorted the values and done the plot. They're already sorted. Let's look at a plot of this and see what the plot looks like. Let's go ahead and compute a histogram. And I'm not going to worry about anything else right now. And I'm going to use histogram because I have a pretty large data set. Okay, there's a lot of values. And the histogram is very interesting. So the histogram kind of goes along with this, right? The majority of the data values are at 0 and the median's at 0. And this is how we compute the mean and the median using StatCrunch. So, what does the center mean? I want to come back now to this hypothetical problem with Mr. Burns. So we recall that Mr. Burns was now running, a manufacturer of clothing store in Burundi. He was marketing this new type of tennis shoe called Psyche, right? And here's the actual data about his employees and their compensation. So he has 9 employees. He pays $1 each an hour, and he pays himself $991 an hour. And like we said, social media, gets a hold of this. They hear reports that he's doing bad things, and they say he runs a sweatshop. Mr. Burns immediately goes on the defensive and says, no, that's not true at all. In fact, the average salary is $100. I should be considered a hero, right? I'm helping all these people because this is really high even for an American worker. And we ask this question: who is right? Okay, let's take a look at the different ways that we can compute the center of the data set to try to understand what it actually means. So this is our data. Let's look at the mean. So I'm going to add all these values together, and I'll get 9 here when I add the ones, and add this to 991, I'll get 1,000. Divided by 10 is $100. So Mr. Burns is not lying. He's telling the truth. But what is the median? Well, I have 10 data values, so the median is the average of the 5th and the 6th data value, which both are 1. So that's going to be my median. When I have an even number, I take the average of the 2 middle values. Makes sense, right? So let's look at these two things graphically to try to understand what we're talking about when we say the center of a data set. Here's a dot plot of the data values. We only have 10 data values, so we make a dot plot. The median is 1, and the mean is 100. Now, this raises an interesting question of what does the center mean? So we're going to say that the center of the data set is the value that most of the data values are centered around. So you can clearly see that the appropriate measure we should use for the center of the data set is the median, because this is really the value that most of the data values are centered around. So this, in a sense, is representative of where the center of the data actually is, which is not necessarily the same as the mean. So Mr. Burns was technically correct. He was not lying. But on the other hand, he was being deceptive, because the center, in order for the center to really be representative, for the data values to be clustered around it, right? We'd have to have a whole lot of workers making around $100, and we don't. What's actually happening is this value is an outlier, and that outlier is acting to pull the average out. If I took 991 out and computed the average, I would get 1. So outliers have a tendency to inflate the average. And this is what Mr. Burns is doing. In the discussion, we're going to look at another example, and this is a real-life example involving a labor negotiation. So which ones do we use? Okay, so what we're kind of seeing is that the mean is inflated, or sometimes it can actually be decreased if the outlier was a lower outlier. So the point is that it's affected by extreme values. And this means that whenever we have outliers, we generally use the median. We don't use the mean. We saw in Mr. Burns's case what happened with that outlier is it took the mean and it inflated it. And now if we use 100 for the center, we're not really being truthful. But also we can have data that has tails. Okay. And we call this skewed data. So skew is a statistician's term for tail. So for example, I can have a data that's left skewed, and we'll talk about this more in the next video, but it has a tail on the left. And what generally tends to happen is the mean gets pulled out towards the tail. So the tail, in a sense, kind of acts like an outlier, you could say. And of course, the same thing would happen if we had a right-tailed or a right-skewed data set. The median would, again, kind of be in the center of the data where most of the data values are clustered around, but the mean would get pulled out, okay? Now, it's important to understand that this is not a mathematical fact. This is what generally tends to occur, and this is what generally tends to occur with financial data. However, there are variables. There are types of quantitative data for which just the opposite is true. The median is out in the tail, and the mean is more towards the center. So don't always suppose that it's true. You really want to compute both. And again, for the sort of data we're going to be looking at, this does tend to be true. When we have symmetric data, in other words, the data looks kind of like a mirror image around some axis of symmetry here. When we have something like this, the mean and the median are basically on top of each other. You can see that this is going to be the median because roughly 50% of the data is below it and 50% is above. And you can also see this will be the mean because there's roughly the same number of data values on both sides, and they're going to average out to this value, the mean in the center. So why is it important? One of the reasons it's important is because skewed distributions are very common. So very often students come into this class and they know what the normal distribution is, and they sometimes think everything has a nice bell-shaped curve. That's what a normal distribution is. It's a nice symmetric bell-shaped curve. IQ, for example, has a normal distribution. But there are a lot of variables that are not. And this is a consequence, at least in finance and economics, of Pareto's principle that I discussed really briefly when we were talking about categorical data plots. There's this thing called the 80-20 law. It says 80% of the contributions are made by 20% of the people. And this occurs a lot when you're looking, again, at any sort of income involving compensation, wealth, anything of this nature. You can see, for example, this is a distribution of the world GDP. This is a little bit of an older chart. It's actually changed since then. But the richest 20% of the nations make up roughly 80-some% of the income. And so very often people think that capitalism is evil because we have these sorts of inequalities. And while you can debate over how this distribution should be, now people claim it's more like 90-10 or 95-5, okay? Even though you could debate that. The reality is it's a mathematical consequence of capitalism. You're always going to have this sort of inequality of wealth distribution. So if you want capitalism, you're going to have to go along with this sort of situation. And so since this is a business class, we're going to deal with a lot of things like this. And we'll talk later on when we discuss shape, when these different types of shape data occur. So let's kind of consider an example in real life that might happen. So it's known that home prices, this is financial data, tend to be right skewed. In other words, there are a few homes that cost a lot of money, and most of the other homes are kind of below it, kind of clumped together. So in other words, home prices tend to look like this. If we look at the graph on the right, so the median is going to be less than the mean. It's right skewed. It has a right tail. And we want to think about how people could potentially misuse this fact. So suppose a real estate agent is trying to sell you a house. Which value do you think they'll use for the center of the data set, the median or the mean? Let's suppose your city is having a meeting to decide how to assess property tax. So you're here at some city council meeting and you're trying to lobby for how the county is going to assess taxes on your property. Which value would you urge City Hall to use? The mean or the median? So, good statistical practice, all right? We know that we either are going to use the mean or the median. We're not going to use the mode. And which one we use depends on outliers and symmetry. So when we have outliers or we have strong skew, we tend to use the median. When our value is, when our distribution is symmetric, we tend to use the mean. And when we're not sure, so for example, you might say, well, in a very large data set, is one outlier going to change things considerably? And the answer is probably not, okay? So when in doubt, compute both, and then basically you see if the values differ by, say, more than 5%, okay? Whether appears to be a significant difference. Or we can actually trim the data set. And we can look at the middle 90% and see if the mean and the median are different. And so we can do this actually for the Major League Baseball. We just computed the mean and the median a second ago. We can go back to that. So one of the questions is this value significantly different than the median? Do these appear to be really different? And you can notice if you look at this data that home runs go out to, roughly, with the exception of Babe Ruth, who's an outlier, right? The home runs are roughly around, say, up to about 20. So this is roughly, 1.3 over 20, okay? And so it's, roughly 5% of the range without Babe Ruth. So we might say that these values are somewhat close enough. But again, if I wanted to be careful, I definitely use the median. Because why? I have skew and I have an outlier. It's a little hard to see here, but I also have an outlier. So the safe choice here would be the median because of the skew and the outlier. And you can see the outlier if you look at the bar plot. I'm sorry, if we look at the box plot, right? If we look, whoops. I did what I said, right? I said bar plot and I hit bar plot. If we look at the box plot, we can see Babe Ruth. Notice how the box plot really accentuates this outlier, where it's hard to see actually in a histogram because it's just this little bar out here and we can't really see this well. And this is why it's called exploratory data analysis. Okay, we like to explore and kind of see which way of presenting the data is best. So here a box plot might be a little better. And we can go ahead and put these two things so they're both horizontal and kind of compare them. But again, that really strong skew and that outlier would suggest that we should use the median and not the mean. Here, we'll put these on top of each other so we can kind of compare them. And you notice actually there are a lot of outliers. And so we're going to talk about how we diagnose outliers, okay? So Babe Ruth is an actual outlier. These data values, even though the box plot indicates they're outliers, they're what we call outliers in name only. They aren't actually outliers. Okay, that pretty much concludes everything we need to know about the center of the data set. Now we're ready to talk about the spread of the data set. We want to know how spread out the data values are. And so it turns out there are, again, 3 potential ways that we can give the spread of a data set. And that should be spread and not center, okay? So you can correct that. And they are the range, the standard deviation, and the interquartile range. And the 4 questions we want to answer is, what are they? We're going to define what they are. How do we compute them? Which one do we use? And why are they important? So this should be changed to range, interquartile range, and standard deviation, sorry. The sins of cut and paste, right? So the range is essentially the length of the interval that contains the entire data set. So it's the maximum minus the minimum data value. The standard deviation is a little difficult to explain, but the way we're going to think of it is it's the average distance. It's a measure of the average distance of the data values from the mean. And we're going to start thinking more and more in this class as the mean is kind of like being an origin, like home base. So this, in a sense, is the average distance of the other data values from home base. And the interquartile range we already discussed is essentially the length of the box, okay, or the third quartile minus the first quartile. How do we compute them? In StatCrunch, using exactly the same method. All we do now is when we choose our statistics, instead of choosing the mean and the median, we just compute the interquartile range, standard deviation, and the range. So let's see how this works. So we go back into StatCrunch here. And I'm going to put these off to the side, scrunch these down. So stat, summary stat, in columns. My quantitative variable is home run. And so here's the standard deviation. I'm going to click on that. Then I'm going to hold the control button down. And I want the range. And then finally, IQR, the interquartile range. And there we are. Notice how different these numbers are. And they're all supposed to represent the spread. So an obvious question is, which one do we use? And the answer to that question is exactly the same as how we determined what to use for the center of the data set. It'll be dictated by the presence of outliers and skew. So the range, I'm going to make a comment about the range. It's always good to compute the range, particularly because you want to know the smallest and the largest value, especially when you're data cleaning. We never use it, however, as a measure of spread. So notice the reason why we didn't use the mean for the center of the data set, because it was very sensitive to outliers. In the case of that Mr. Burns scenario, one data point caused the center to change 100 times. Okay, without Mr. Burns's salary, the mean would have been 1. We put it in, all of a sudden the mean is 100. And we don't like that. So we like our summary statistics to be robust. In other words, they're not affected by just one data point. And what does the range use? Well, the range uses the most extreme data values, right? If I took out Babe Ruth, the next highest person has 19 home runs. Now the range is 19. It went from 19 to 54, which is roughly, what, a factor of 3. So we don't use the range. We generally compute it, but we don't use it to specify the spread of a data set. The interquartile range we use very much like the median when we have a relatively strong skew or we have outliers, and the standard deviation is good for when we have symmetric data. And this is a little table that we can use. Okay? So this talks about the shape of the distribution. Outliers or strong skew, we use the median, and the spread, we use the IQR. The median's the center, the IQR is the spread. When our data set is nice and symmetric, okay, we use the mean for the center, standard deviation for the spread. Okay, why is this important? So let me give you a kind of funny hypothetical example. So suppose we have two, average everyday American assassins here, Jack and Jill. Remember Jack and Jill when you were, in grade school, right? And Jack still has issues about Jill because he fell down the hill and he kind of blames her, and he still has a little grudge against her. And so he's going around telling people that he's a lot better than Jill. He says, I'm a 10 times better, assassin than Jill is. And Jill's like, okay, let's see what you got. And so they're going to go to a shooting range and they're going to see who is the better shot. So they're going to go to, if you've seen like in the circus, for example, or fairs, they have these sort of moving targets, right? And you try to hit them. And what they're going to record for each of these people, Jack and Jill, is they're going to record how far off to the left or right they were from the bullseye. Okay, so Jill goes first, ladies first, and her first shot is 0.4 inches, we'll say, and it's positive because it's to the right. And then she's 0.1 inches to the left of the bullseye on the second duck, and 0.4, and then 0.5. And now Jack goes. We can see he's 6 inches off to the left on the first one, then 3 inches off to the left, 4 inches to the right, 5 inches to the right. And Jill thinks it's over, right? She's like, man, I totally cremated Jack, right? But then her friend calls her up and says, hey, guess what? Jack's on social media saying that he's better. And sure enough, she goes on and she finds out that he's saying that, her average distance off from the target was 0.2, and I guess I'm gonna have to change that from inches to centimeters, right? It doesn't really matter for the purpose of this discussion. So he says, her average distance was 0.2 centimeters off, and mine's 0 centimeters off, so it was close, but I'm still the better shot. And Jill's going, what the heck? Is Jack correct? Yes, he is. Just like Mr. Burns. Okay, Jack is correct here. But his interpretation of what happened correct. And it's no. And this has to do with the spread now. Okay? It doesn't have to do with the skew. It has to do with the spread. And let me show you why. So, the spread reflects how far off the data values are from the center, right? So this is Jill's data, and this is Jack's data. Notice Jack's telling the truth. Okay, his average, in fact, is 0. The problem is his values are so spread out that 0 is not representative of what we expect to get on a single shot. Whereas Jill's are really tightly clustered, right? Like she may not, hit the person in the heart, but she's going to take on a major organ and still kill him, right? Whereas Jack, he may end up hitting the person next to him. So this spread of the data is really important. It tells us how representative the center really is of what we'd expect to see if we did a single trial. If Jill shot once and if Jack shot once. So you notice it isn't the shape of the data. They're both symmetric. It's the spread that makes Jack's data misleading here, okay? So again, low spreads, you're tightly clustered around the mean, and that means the mean is going to be representative, okay? We really think that 0.2 is representative of what we would see if Jill shot one time, okay? Whereas with really high spread, there's so much variability, we don't know what we're going to get, right? Jack may hit in the center, it's possible, but like I say, it's also very likely that he's going to hit somebody next to him and not even hit his target, right? So this is a kind of fun example, but why do we actually care about this? Well, we care about it because variability is incredibly important in business. Okay? Variability is the opposite of consistency. And I will tell you a fact. I used to give this in lecture. I don't have the data right in front of me. If you look at the top 10 fast food companies, McDonald's makes more money than the other top 9 combined. And there's a reason why. And if you ever watched the movie with Michael Keaton about McDonald's, you know exactly what that reason is. Because McDonald's has perfected the art of mass production. Every burger they make is very consistent. So you can argue that it's crappy food or not good for you or whatever, right? But the whole point is you get the same thing every time you go. You know when you go to McDonald's, you're going to get the same hot cup of coffee. You're going to get the same cheeseburger or whatever because they want things to be consistent. Walmart is the same way. You go in, everything is laid out the same in every store. Why? They want consistency. And so to kind of show you why that might be important, you might say, well, who really cares, right? I'm going to go ahead and look at this data set, paints. This is the other data set that you downloaded. And there are 2 brands of paints. And so each of these is one paint. So I'm testing 1, 2, 3, 4, 5, 6 batches of each brand. And for each test, we're looking at how many months the paint lasts before it fades, right? So the first batch of brand A lasted 10 months before it faded. Okay. The first batch of brand B lasted 35 months before it faded. And the answer is, which one's better, okay? So let's go ahead and look at this data set and try to determine. So we'll go into StatCrunch. And what I'm going to do is I'm going to make a dot plot, and we're going to talk about this later on, but I'm going to make a dot plot where I'm grouping with respect to these 2 brands. Let me see if I can do this. I think I can. No, I'm not going to be able to do it. I'm just going to stack them on top of each other, okay? So let's go ahead and plot both of these variables. And I'm going to stack them on top of each other. And we can put the mean and the median in. Okay, won't do any harm. And I'm going to have 2 rows per page, and I want them to use the same x-axis. In other words, I want these 2 dot plots stacked on top of each other, and I want their x-axes to line up so I can make an apples-to-apples comparison. And let's look and see what these 2 things look like. Notice, just like with the Jack and Jill example, the data sets are symmetric. The mean and the median actually lie on top of each other. That's why you can't see 2 different colored bars here. However, if we look at the spread, we see that brand B has much less variability, whereas brand A has a lot of variability. Why do we care? You might say, hey, that's really good, because someone might get a brand A, and it'll last 60 months, and that's so much better than brand B. That's true. However, as a customer, what if you get that 60-month batch one time, and the next time you get the 10-month batch? Man, you're not going to be happy. And here's the thing, Pareto's principle kicks in here. A small percentage of your customers are going to constitute the majority of your complaints. So what's going to happen with this person that gets 10 or maybe 20 months? What are they going to do? Their dissatisfaction is going to be amplified through social media. And this has a huge effect. When you look at ratings on Amazon or Netflix or anything, these highly influenced customers, to the point where other companies actually devise bots and ways of giving negative reviews that appear like they're from a human. And so companies actually spend a lot of time doing, I guess you could say, counterintelligence. They try to infer what is a real complaint, and they should really take seriously and use that to improve their product, versus what is a fake complaint, because this has such a strong influence. And we're all influenced by bad ratings. But this is the problem. These guys are going to be amplified, and we don't want that. We want the customer, every time when they buy something, they know exactly what they're going to get. So this is a really important point. So variability in business is bad. We want consistency. It's also true in finance. So if you know anything about economics or finance, you hear about this word volatility. Volatility means risk in the market, right? And so if you look at stock prices and you look at the S&P, so what they do is they take the logarithm of the closing price divided by the opening price. So this is the S&P on a certain day, the closing and the opening. They take the ratio and they take the log, and this is called the volatility. And when when these values begin to spread out a lot, the volatility becomes high, people pull out of the market. And so there are quants and financial analysts that look at this sort of stuff very closely. So spread is really important. We want to know how spread out the data values are. Okay, that's it for this video. In the next video, we put it all together. We learn how we take this visual summary we made in the plot, and how we take this numerical summary that we made in the summary statistics, and we bring them together and describe the entire data set nice and simply. Thanks for watching, and I'll see you in the next video.